$3. That's what it costs to buy a small bag of powder that chemically converts rust into a permanent paintable waterproof shield. No grinding, no sandblasting, no bare metal required. You mix it with warm water, brush it onto a rusted surface, and within 15 minutes you watch the corrosion itself change color, from sickly orange-brown to a dense blue-black. That color change isn't cosmetic. It's a molecule rewriting itself. And the compound doing it isn't some new lab breakthrough. It's something tanners, blacksmiths, navies, and armies have been quietly using for centuries, long before anyone understood why it worked. Here's the problem most people are dealing with instead. Rust doesn't just sit there, it eats. A flaking patch on a truck frame, a garden tool, cast iron pan, or an old gate hinge keeps spreading as long as oxygen and moisture can reach bare iron. The standard fix sold to you is either grinding the metal back to shiny bare steel, which is slow, messy, and often impossible, on something like a frame rail you can't fully access, or spraying on a synthetic rust converter or primer that sits on top of the corrosion like a bandage. Bandages fail. Moisture finds a hairline scratch, works underneath, and you're back where you started, except now you've also spent $30 or $40 on a bottle that's mostly solvent. What almost nobody realizes is that the active ingredient doing the real work in a lot of those bottles is something you can buy in bulk, in its plain natural form, for a fraction of the price, because the chemistry was never really about the bottle. It's about a class of plant compounds called tannins, and specifically the purified form known as tannic acid. The story starts, unglamorously, in a tanning vat. For thousands of years, turning raw animal hide into durable leather meant soaking it in water full of crushed oak bark or other tannin-rich plant material. The process is literally where the word tanning comes from. Anyone who worked around those vats for long enough noticed something odd. Iron tools that fell in, or buckles and blades that got splashed, stopped rusting the way they should have. Instead of the usual orange bloom, they picked up a dark, tough film that shrugged off moisture. That kind of observation travels fast in any trade that depends on tools not failing, and across a lot of ironworking cultures, Roman era, blacksmiths, later European armories, and elsewhere, bark and gall extracts became a known, if informal, way to keep iron and steel from rotting in damp storage. The same basic discovery shows up again, independently, on the other side of the world, in feudal Japan. Katana blades have a soft iron core wrapped around a harder steel edge, and that softer core is genuinely vulnerable to Japan's humidity. Traditional swordsmithing and woodworking crafts developed kakishibu, fermented persimmon juice, rich in tannins, as a coating brushed onto blades, tool handles, and even paper and cloth to resist moisture and rot. It's still used today by some traditional craftspeople for exactly that reason, and in South America, quebracho, one of the most tannin-dense woods on the planet, became and remains a major industrial source of tannin extract used in leather tanning and metal treatment, precisely because the compound is so concentrated in it. Nobody in any of these traditions could explain the chemistry. That had to wait for modern organic chemistry to catch up. Chemists working in the late 1700s and early 1800s began isolating and naming the tannin family of compounds. And by the 1830s, tannic acid itself had been isolated as a distinct purifiable substance. Once chemists could study it directly, the mechanism became clear, and it's genuinely elegant. Tannic acid reacts with iron oxide, ordinary rust, and converts it into a different compound entirely, called ferric tannate. Ferric tannate is dark, insoluble in water, and chemically stable. Critically, this is a conversion, not a coating. A synthetic primer sits on top of rust and hopes moisture never reaches it. Tannic acid reacts with the rust that's already there and turns it into part of the new protective layer. The corrosion becomes the shield instead of the threat. This is also why the military took an interest. Corrosion has always been a logistics problem in war. Equipment shipped through humid or salty environments seizes up, and gear that won't move or fire is useless regardless of who's holding it. Through the 19th and 20th centuries, navies and armies experimented constantly with anti-corrosion treatments, from galvanizing to specialized paints to natural tannin-based compounds, testing what held up under salt exposure and what didn't. Tannin chemistry was one of several approaches in that toolkit, valued for being cheap, plentiful, and effective enough for field conditions, though it was never the only method in use, and plenty of that era's corrosion protection came from other approaches like galvanizing and oil-based coatings instead. So if this stuff works, and it's been known for centuries, why isn't a $3 bag of tannic acid sitting next to the WD-40 in every hardware store? The honest answer isn't a hidden conspiracy, it's just how the market for rust protection actually developed. Tannic acid is a naturally occurring compound. You can't patent it, and you can't build an exclusive product line around something anyone can buy in bulk and mix in a bucket. Meanwhile, the companies that built the modern rust converter and undercoating industry spent decades investing in synthetic formulations, branding, and distribution, and pure tannic acid became one ingredient folded into a marked-up, solvent-diluted retail product, rather than something sold plainly on its own. If you actually flip over a bottle of commercial rust converter and read the safety data sheet, tannic acid is very often listed right there as the active ingredient. It just isn't the headline on the label. None of that means the commercial products are a scam. Some do add genuinely useful stabilizers, surfactants, or shelf-stable formulations that make application easier. And for extreme environments, constant submersion, high heat, heavy chemical exposure, a specialized industrial product is the right call, not a DIY mix. But for the rust, most people actually deal with a truck frame, hand tools, cast iron cookware, an old gate or fence, farm equipment. The core active chemistry is the same thing you can buy plain for far less. Here's how to actually use it. Buy food-grade tannic acid powder. It's available from grocery or health food suppliers and online bulk sellers, usually a few dollars, for a bag that will treat a large surface area. Mix roughly 4 grams of powder into 100 milliliters of warm water and stir until it's fully dissolved. It should look like strong black tea. Take a wire brush or coarse steel wool and knock off any loose, flaking rust. You do not need to grind down to bare, shiny metal because the solution actually needs existing rust to react with. Brush or spray the solution evenly over the surface. Within 10 to 15 minutes, you'll see the color shift from orange-brown to dark blue-black. That's the conversion happening. Let it air dry fully, generally 2 to 4 hours depending on humidity, then apply a second coat for better depth and coverage. Once that's cured, the surface is stabilized and ready for a top coat, paint, oil, wax, or rubberized undercoating, depending on what you're protecting. For tools, a light coat of boiled linseed oil or beeswax afterward adds extra water resistance. For cast iron cookware, treat just the rust spots, wash thoroughly, and reseason as normal. One safety note worth taking seriously. Tannic acid is food grade and non-toxic at normal concentrations, but at the strength used here, it can irritate skin and eyes. So wear gloves and avoid splashing it around, especially near your face. And be realistic about limits. This converts existing rust and protects the surface going forward, but it isn't magic. The deeply pitted or structurally compromised metal still needs mechanical repair, not just a chemical treatment. What's actually interesting about this whole story isn't that someone is hiding a miracle cure from you. It's that a genuinely useful, well-understood piece of chemistry got buried under decades of repackaging and markup simply because it was too cheap and too unpatentable to build a business around. The fix for that isn't outrage. It's just knowing what to look for on the label and knowing you can mix the same reaction yourself in your driveway for the cost of a coffee. This has been Hidden Fix Lab. If this changed how you'll look at that rusted axe head, gate hinge, or truck frame sitting around your place, that's the whole point. See you in the next one.